Hi, welcome back to es346 Basic Thermodynamics. This is Module 8.5 on exergy transfer. Sections in the textbook are 8.6 through 8.8. Here are the two learning outcomes. At the end of the module, you'll understand the concepts of exergy transfer and exergy destruction, and you'll be able to calculate the lost work potential in the heat transfer process. I want to talk a little bit about this idea of exergy transfer. So let's just imagine now that I have a hot block, and then I'm going to go ahead and place it right next to a cold block. And we know that hot energy goes from hot to cold. There'd be some amount of energy that would go from the hot block to cold block. And we've seen this generates entropy, and not surprisingly, we'll see that this destroys exergy. If I wanted to know the amount of heat, I would use the first law. So Q would be equal to the mass of, I'll go ahead and call this block A and this block B. That would be the mass of A times the heat capacity of A, T2 minus T1A. And that's the same heat that goes into this block, which would be the mass of block B, of B, heat capacity of B, and that would be T1B minus at final temperature T2, and at point T2 they're in thermal equilibrium. If there's an entropy generated, we've seen this before, we can calculate delta S, and delta S would be the mass of block A, heat capacity of block A, then we have these log of T2 over T1A, and then we need to add the mass of block B, heat capacity of block B, natural log of T2 over T1B. And we know that that right there is not equal to 0. In fact, we know that that's going to be greater than 0 because some entropy is going to be generated. So we have energy being conserved as we move across. We have entropy being generated as we go up, and it turns out that then as we go across here, we have exergy being destroyed. And one way to kind of draw this schematically, this is from a diagram in the book, I think it's pretty good. This is our hot block and our cold block. You think of these arrows as an amount of quantity. There's the internal energy, and it's moving from the hot block to the cold block, and it's conserved. The entropy, as it gets into the cold block, increases. So kind of the size of the arrow increases, and the exergy does the opposite. We have a lot of exergy, and then it gets destroyed as we move across. So you can kind of look in here, we have entropy generation and exergy destruction going on in this irreversible process. So here let's do a numeric example, and what I want to know is, what is the lost work potential in this countercurrent steam heat exchanger? It's at a constant pressure of 100 kilopascals on both sides. So I have some hot steam coming in at 300, getting cooled down to 200, being done with some somewhat cooler steam at 150, and it's got an outlet temperature that I need to go ahead and calculate over here. And so we'll assume that these flow rates are the same. So I'm going to have m dot of stream A equal to m dot of B. So this would be stream A, and this would be stream B. And so we've got heat going from the hot stream into the cold stream. And under these conditions here, actually, I can actually approximate steam as an ideal gas, and these temperature changes aren't very big, so I'll say that Cp is essentially equal to a constant. And the heat capacity of steam is 1.87 kilojoules per kilogram Kelvin. And if we want to calculate the amount of exergy destroyed, we need to go ahead and calculate the amount of entropy that's being generated. So let's calculate delta S. And delta S is, for an ideal gas, Cp ln of T2 over T1 minus R ln of P2 over P1. And it's a constant pressure, so that term right there is going to be equal to 0. So we can go ahead and put in my value here. Cp of steam is 1.87. Natural log of this is 473 over 573 for one stream, and plus 1.87. Natural log on my other stream is 523 over 423. And that entropy that's being generated is 0.0381. That will be kilojoules per Kelvin. So now to calculate the exergy being destroyed, call it XCD, we know that that is T naught delta S of my stream here. And so my environment conditions are 298, 25 degrees Celsius, times that 0.0381, and that comes out to be 11.4 kilojoules. So that's not the amount of energy being transferred between this. This is the amount of exergy being destroyed. The amount of exergy that went through is going to be a much larger number than that. But what does this 11.4 represent? And one way to think of it is, if this was that hot stream and this was that cold stream, and instead of just putting them in a countercurrent heat exchanger, I'd put a heat engine in between them and pulled out the requisite energy from the hot stream, but generated some work and then dumped the rest into the cold stream, I would have some work here. Now, I haven't accomplished the same thing that I want up here because this cold stream didn't get as much energy. But what I could do now is take this work, run it through a heat pump to put the remaining energy into the cold stream, pulling that from the environment. And it turns out it isn't going to take all of that work, and so I'd get this extra work, and that's the 11.4 kilojoules that I have from that stream. So this 11.4 is the exergy that was destroyed. I could have saved it if I'd done it with a different process, essentially a bunch of reversible heat engines, in this case a heat engine and heat pump.